Well, since we have q analogs of integers and q analogs of factorials, you're probably wondering if there's q analogs of binomial coefficients. And in fact there are. So let's look at those. So we define the q analog of a binomial coefficient in the obvious way. So if there's n on top, we've got quantum n factorial on top, and then k on the bottom, we've got quantum k factorial times quantum n minus k factorial on the bottom. And since we usually put binomial coefficients in a Pascal's triangle, I suppose we could put these in a quantum Pascal's triangle. Now if k is 0, quantum 0 factorial is 1. So we've just got nq factorial over nq factorial, so that's going to be 1. And then if k is n, same thing happens. So we're going to have 1s all the way down the outside. And so the first one that's neither of those is quantum 2, choose quantum 1. So that's 1 plus q over 1 times 1. So it's just 1 plus q. Let's do another row. So here we are, quantum 3, choose quantum 1. So quantum 3 factorial over quantum 1 factorial. Quantum 2 factorial is 1 plus q squared divided by 1 plus q. Oops. Times 1 plus q divided by 1 plus q. So that's just 1 plus q squared. And by symmetry here we've got 1 plus q squared again. I guess in general, if we have quantum n choose quantum 1, that's going to be quantum n factorial over quantum 1 factorial times quantum n minus 1 factorial. We'll get a lot of cancellation here, leaving us just with quantum n on top. Because quantum n minus 1 is going to cancel, quantum n minus 2 is going to cancel, etc. So we're just left with quantum n. So I guess we can continue one step down pretty easily, because this is going to be quantum 4, choose quantum 1. So that's 1 plus q squared plus q cubed. And then over here, 1 plus q squared plus q cubed. And now we come to the first really interesting entry, which is quantum 4, choose quantum 2. So we've got 1 plus q squared plus q cubed over 1 plus q squared over 1 plus q divided by 1 plus q times 1 plus q. Quantum 2 factorial times quantum 2 factorial. Those cancel. And if we write out what's on top, oh, actually, let's see. This is 1 plus q times 1 plus q squared, isn't it? 1 plus q times 1 plus q squared would be 1 plus q squared plus q cubed. So that means that we can cancel this and that and make this a 1 plus q squared. And then there's nothing left to cancel on the bottom, so what goes here is 1 plus q squared times 1 plus q squared. So 1 plus q squared times 1 plus q squared equals 1 plus q squared times all of this, q squared plus q cubed plus q to the fourth. So this is 1 plus q plus 2q squared plus q cubed plus q to the fourth. So this is the first entry of Pascal's triangle that isn't equal to just the q factorial of an integer. This is not, so 4 choose 2 is 6, but this is not the q analog of 6. It evaluates to 6 if we plug in q equals 1, because we'll have 1 plus 1 plus 2 plus 1 plus 1, but it's not the q analog of 6, which is the sum of all powers of q up to q to the fifth. So it's the first time in the q Pascal's triangle that is different. Now there is a recurrence formula that we can use to get one entry in terms of the 2 above it. So it turns out that quantum n choose quantum k is q to the n minus k quantum n minus 1 choose quantum k minus 1 plus quantum n minus 1 choose quantum k. So we don't need a power of q there. So it's almost like the regular recurrence, except that we've got a power of q next to the left number that we're going to add if we're adding two things together. And we can prove this just by plugging and chugging. So actually it will be convenient if we multiply both sides times by quantum k. So let's look at quantum k times the left-hand side. Actually, quantum k factorial times the left-hand side. So that is quantum k factorial times quantum n factorial over quantum k factorial quantum n minus k factorial. These cancel. So that equals this fraction. That cancels with that. And then a lot of factors of quantum n factorial are going to cancel with this. And that leaves us with quantum n times quantum n minus 1 all the way down to quantum n minus k plus 1, the last factor of quantum n factorial that doesn't cancel with the bottom. Now let's look at quantum k factorial times the right-hand side. So, well, this factor is, this sum and is going to be sort of easy to analyze. So that's quantum k factorial times quantum n minus 1 factorial over quantum k factorial quantum n minus 1 minus k factorial plus something. So this part is going to be, these cancel, and then again quantum n minus 1 minus k factorial is going to cancel lots of the factors here, and we're going to get n minus 1, quantum n minus 1 all the way down to quantum n minus k. That's the last factor on top that doesn't cancel with what's on the bottom here. So Well, this much is equal to that expression. Plus, let's see what else we have. Q to the n minus k times quantum k factorial times quantum n minus 1 factorial over quantum k minus 1 factorial times quantum n minus 1 minus k minus 1. So n minus k factorial. So that's q to the n minus k times quantum k factorial and quantum k minus 1 factorial mostly cancel. And we've got just a quantum k left on top. And then these mostly cancel. And we have quantum n minus 1 down to quantum n minus k plus 1. Alright, so that much is equal to this. We're adding these two things, and we've reduced that to the sum of these two expressions, which have a lot of factors in common. They both have n minus 1, n minus 2, all the way down to n minus k plus 1. This one doesn't quite have n minus k in it. It stops right before that. So this gives us, factor out n minus 1 quantum all the way down to n minus k plus 1. And then we'll have n minus k from here that doesn't cancel, plus q to the n minus k quantum k factorial. Oops, just quantum k. Alright, so comparing to the other expression, we've got quantum n minus 1 product down to quantum n minus k plus 1. So I'm hoping if this turns out to be quantum n, then we're all set. So what is this? This part is 1 plus q, all the powers up to n minus k minus 1, that's the first part, plus the powers of q from 0 to k minus 1 with n minus k added. So q to the 0 plus n minus k plus q to the 1 plus n minus k all the way up to q to the k minus 1 plus n minus k. So we've got powers of 0, 1 up to n minus k minus 1. This is n minus k, that's n minus k plus 1. And this last one, well, the k and the minus k cancel. So this is q to the n minus 1. So this whole expression is quantum n. So in fact, quantum k factorial times the right-hand side is equal to quantum k times the left-hand side. So we do have this recurrence relation for the quantum binomial coefficients. And one kind of neat fact about the quantum binomial coefficients is that Q analogs often come up in non-commutative settings where we have ordinary integers in commutative settings. So if we look at, let's consider in non-commuting variables x and y whose coefficients are polynomials in Q. And let's look at the quotient of this ring. So non-commuting polynomials in non-commuting variables x and y whose coefficients are polynomials in Q with complex coefficients, modulo the ideal yx minus qxy. So when we take a quotient of a ring by an ideal, that's saying that everything in the ideal gets set to 0. So we're saying that yx gets set to equal to qxy. So basically you can write every monomial in this ring with the x's before the y's. If you ever see a y before an x, you can switch them and put a power of q in there. So if we look at x plus y squared, that's x plus y times x plus y. That is x squared plus xy plus yx, which we can't immediately combine because x and y don't commute, plus y squared. We get x squared plus this yx becomes a qxy by this relation, plus y squared. So that's x squared plus 1 plus q xy plus y squared. And this 1 plus q happens to be equal to the q analog of 2 choose 1. Or perhaps better said, quantum 2 choose quantum 1. Because, as we saw in Pascal's triangle, quantum n choose quantum k is not in general equal to the q analog of n choose k. There's a general fact that in this ring, polynomials in two non-commuting variables x and y whose coefficients are polynomials in Q, that we have x plus y to the n is a sum as k goes from 0 to n. Not n choose k, but quantum n choose quantum k, x to the k, y to the n minus k. And I'm going to let you guys do that for homework for the proof. The end.